And second application, second application will present the use of developed signal analysis technique for diagnosis of glaucoma. So with this background, let us start this talk. So this is the overview of this talk. First, we will see introduction, and after that, we will see a brief overview of the Fourier transform. And after that, we will see Fourier-Bessel series expansion, and then this Fourier-Bessel series expansion based method, which we call Fourier-Bessel series expansion based empirical wavelet transform, that is FBSEWT, will be explained. And after that, we will see the two main applications of this work. One is for diagnosis of alcoholism using EEG signals, and second one is diagnosis of glaucoma using fundus images. That will be explained. And after that, conclusion will be provided. So transform, actually, it is very commonly used signal processing, signal processing approach, and that nearly has touched most of the areas of science and technology. It is very difficult to find any area where we don't use transforms. So this actually what it does, it takes signal from one domain and it maps to other domain. So it converts from one domain signal to other domain signal. For example, Fourier transform. So it converts signal from time domain to frequency domain. And this transform has actually some advantages. So by doing transformation, we can go from one domain to other domain, and we do some suitable processing. And after that, we can come back in the actual domain. So we will highlight some of the advantages here of the transforms. So let transform provide hidden information about the original function of the signal, like what are the signal, what is the minor frequency of the signal, what is the frequency component corresponding to signal, what are the frequency components corresponding to noise. So all these informations, actually that is not possible due to time domain representation, that is actual domain. But when you go in frequency domain, another domain, then such kind of information easily can be obtained. And this transform also helps you solve differential equations. So like what we do actually, the signals, whatever we encounter in real life, we consider them as the output of the system. And the system we represent with the help of mathematical functions. And this differential equation is one kind of such mathematical operation which is used to represent the linear time invariant system. And this differential equation, if you want to solve in the time domain, it is very time consuming task, and it may be difficult also. But when you go in frequency domain, and nicely you can solve the differential equation, nicely you can understand the system from which the system signal is generated. And this transform and Laplace transform is one of such transform that help us to solve the differential equation. And the transform also can provide data compression, and storage may require less memory. So in signal transform, the selection of basis functions is very important. And somehow if you are able to select basis functions which have structure similarity like the signal that we want to analyze, then in that way requirement of coefficients will be less. And in that, like if the suitable basis function class has been selected, and nicely we can represent signal with the less memory or with the good compression. And the very good advantage, that is actually one of the beauty of the transforms, that is when you go in transform domain, then time information is lost. So like generally when we do processing or analysis, then we assume that whatever process is actually that is dependent on time. And when you perform transformation, then there is no time information. So you are in such a domain, there is no requirement of time. And so without assuming any condition on time, actually we can do a lot of processing in other domain. So this is actually one of the beauty. And for example, like if you want to implement convolution in time domain, then you have to assume causality of the system. On the other hand, if you use this transformation, then you can convert this convolution problem as a multiplication problem in frequency domain, and nicely you can implement a convolution without assuming any condition on time, and then you can come back in the time domain. So these are the few major advantages of the transforms. And one of the very like commonly your simple transform, that is well-known transform, very old transform, that is Fourier transform. And this Fourier proposed this transform in 1807. And Fourier was actually from physics background. When he was doing experiment on the prism, then this white prism decomposes white light into 7 colors. And this Fourier actually got idea, if this white light can be decomposed into 7 colors, then why we cannot decompose the signal, that is complicated signal, into simple components. So like this is a complicated signal, they're very difficult to understand, they are unknown signals. We can nicely represent them with the help of non-functions, mathematical functions, we call them basis functions. And nicely we can represent unknown problem in terms of simple problem, in terms of non-problems, and we can perform a nice analysis with the Fourier transform. And according to Fourier transform, or according to this Fourier theory, the complicated signal can be represented with the help of sinusoidal functions, or this signal can be represented as a combination of sinusoidal functions. And this actually, so it is a one kind of bridge between time domain to frequency domain, then use analysis process. And if you want to come back from frequency domain to time domain, then use synthesis process. And this analysis and synthesis process can be represented mathematically with the help of two equations that you can see on the slide. The first one is called the analysis equation, and second one is known as synthesis equation. So analysis, what we do, we integrate signal from minus infinite to plus infinite entire time. So there is no time in the frequency domain. And similarly, when we are performing a synthesis process, we are integrating frequency from minus infinite to plus infinite. So there is no frequency in the time domain. So time domain and frequency domain both are disjoint. And here you can see one example where nicely, like three signals in time domain, they have 5 Hz sinusoids, 25 Hz sinusoid, and 50 Hz sinusoids, and the corresponding frequency domain you can see. And there is a peak at a different frequency component present in the signal. So like first signal has 5 Hz frequency, its peak at 5 Hz. Second one has peak at 25 Hz, and third signal has peak at 50 Hz. So this Fourier transform measures the similarity between the signal that we want to analyze with respect to the basis functions that is used. So that particular frequency is present in the signal, that corresponding coefficient will be high. Otherwise, it's corresponding, if the corresponding coefficient is less or really 0, then we call it minor frequency component, which is present in the signal. And this Fourier transform actually is a very well-known transform, but it has got some shortcomings, some limitations, and it is suitable for stationary signals, and it requires the use of window function in order to obtain the spectrum of the signal. And the whatever actually method that we have seen in last slide, it uses actually complex exponential functions to represent the signal. And due to that, there is a positive frequency, negative frequency, both kind of frequencies are present. And other actually problems with the Fourier transform, whatever the basis functions we use in Fourier transform, they are periodic in nature, and they do not converge with time. And the basis functions also, they do not include modulations in the representation. And the spectrum provides actually this frequency points that is actually half of the signal length. So the resolution becomes half. So these are some of the shortcomings, and luckily we have got some Fourier-Bessel series expansion which help us to overcome these limitations. So it doesn't require this Fourier-Bessel series expansion based method doesn't require use of window function in order to obtain the spectrum, and it represents signal in terms of real Bessel basis functions, and it represents in terms of only positive frequency. There is no negative frequency. And these basis functions that we use in Fourier-Bessel series expansion, they are aperiodic in nature and decay with time. So due to that, these basis functions converge with respect to time. And these basis functions don't include a modulation. Actually, they include amplitude modulation, unlike to Fourier transform. And due to that, that modulation damping factor, they are highly suitable to represent non-stationary signals. And since there is a use of real basis functions, so due to that, whatever is the spectrum obtained using ABSC, that actually has double resolution as compared to the Fourier transform. So from where this Fourier-Bessel series expansion has come, these Bessel functions are the solution of the linear second order differential equation that you can see in the slide. And here, the solution of this differential equation, that is can be written in terms of JVX and BVX. And this here, JVX and BVX are the Bessel functions of the first kind of order B. And this order 0 and order 1 of first kind Bessel functions have been used actually for signal analysis application, and they also have this orthogonality condition. They satisfy orthogonality principle, and mathematically this orthogonality principle can be seen using this equation. And you can see these two kind of Bessel basis functions, like 0 order and first order, 1 order of first kind. And you can see from the plots, from the graphs, these basis functions decay with time. So that is a very useful property to represent the real life signals. They also decay with time for kind like a speech signal, biomedical signals, and there you can use of such kind of basis functions. And in this work, we have used two kind of Fourier-Bessel series expansion. First is 0 order, and second one is first order. And you can see in the slide there are mathematical expressions for analysis and synthesis part of the 0 order and 1 order for FBSE method. And this first like AK, these are the coefficients corresponding to 0 order FBSE expansion, and BK are the coefficient corresponding to 1 order FBSE of first kind. And this Bessel functions root can be computed using Newton-Raphson method. And so based on the Taylor series expansion, we can represent this Bessel function with such kind of expression. And then we can use Newton-Raphson method to solve this mathematical expression. And the initial value of the root is selected based on the this beta k approximately equal to k pi rule. And so for example, like if you want to compute first root, then we put k equal to 1, and if we want to compute last k equal to capital N, then we put a capital N. So this method gives you initial roots, and after that initial roots we can determine the final roots or more accurate roots using this Newton-Raphson method. And we have derived relation between this order and frequency of a sinusoidal function. So like if you want to use this FBSE expansion for a particular sinusoidal, whose frequency is 50 Hz, then there is a peak at a particular order in FBSE expansion. And that relation between order and frequency is given by this expression. That is beta k equal to 2 pi f k L upon fs. And here L is the size of the window, and f k is the kth frequency, and f is the sampling rate, and beta k is the kth root. And so this provides a relation between order and frequency for a signal. And so in that way, we can use this Fourier-Bessel series expansion as a signal representation with the help of such mathematical expression in unique way. So this is it can be used an alternate of the Fourier transform with many desirable properties. So now after that, recently there is a signal analysis technique that is known as empirical wavelet transform. So that is in the empirical wavelet transform, it has been shown that it is better than the empirical mode decomposition for signal analysis. So empirical mode decomposition method suffers from the two two limitations. And one is it lacks mathematical theory, and second one, it has a mode mixing problem. So like when you have components from the analysis technique, this one component shows the presence of two frequency components. So due to these problems, there is motivation for developing this empirical wavelet transform method. And empirical wavelet transform, we use Fourier transform based spectrum. And this spectrum so what we have done, we have replaced this Fourier transform based spectrum with the help of Fourier-Bessel series expansion based spectrum. And then we have separated the components using such kind of method. So this FBSEWT method requires three major steps. One, computing the spectrum of the signal, and then we determine boundaries of the spectrum corresponding to the components present in the signal. And based on these boundaries, we design the filters, wavelet filters, and then these filters separate the components, and then nicely we can apply Hilbert transform on these components, and that gives us time frequency representation. So this is this is example. Here you can see one basis function that is itself is a Bessel function, and you see the spectrum using Fourier transform, and which has band pass nature. On the other hand, if you compute the spectrum using Bessel function, then there is only one spectral line. So this represents Fourier-Bessel series expansion based method represents spectral in more compact manner. So entire band of frequencies can be represented by one spectral line. So this is very useful to separate the components on the Fourier-Bessel series spectrum, the FBSE scale. So this is the overall actually block diagram of this proposed method. We have signal, then we have FBSE spectrum, then we use scale space representation of FBSE spectrum, then we detect boundaries of the Fourier-Bessel domain, then we determine filter bank corresponding to FBSEWT method, and then we have separate subbands, and after that we actually apply Hilbert transform, and that is actually in this work we have used normalized Hilbert transform that is better than Hilbert transform for obtaining instantaneous amplitude and instantaneous frequency of these subbands. And then arrangement of these instantaneous amplitude and instantaneous frequency provide us time frequency representation, and which is better than existing time frequency representation. So this is actually one example here. You can see we have seen this 3-component amplitude modulated signal, and you see the spectrum, the first part in the bottom side, that is the spectrum and the design filter bank corresponding to existing EWT method empirical wavelet transform, and right hand side you can see the spectrum, segmented spectrum and design filter bank corresponding to Fourier-Bessel series expansion based spectrum. And you can see FBSE based spectrum is giving better segmentation and better design of filters. And after that, we have also compared time frequency representation of this synthetic signal, which are 3 amplitude modulated signals. And you can see the comparison of Hilbert-Wang transform and empirical wavelet transform with the proposed Fourier-Bessel series expansion based empirical wavelet transform. And you can see from these results, FBSEWT, which we have proposed, provides better time frequency representation as compared to the other existing methods in the literature. And we have also performed this quantitative analysis that you can see from the table, and where in all 3 cases when this different frequency ranges and closeness of the frequency components, our proposed method provides better performance as compared to the other existing methods. After that, we have actually studied this proposed method for real life signals like epileptic seizures. And epileptic seizure, all neurons in the brain, they synchronize together and they generate very high electrical activity. And due to that, there is a presence of spikes in the EEG signal and a large amplitude of the EEG signal. And due to that, if you see the Hilbert-Wang transform based time frequency representation, there is absence of high frequency components. And when you see the time frequency representation based on the empirical wavelet transform, there is still absence of high frequency component. But on the other hand, if you see the proposed FBSEWT method and the obtained time frequency representation, which has nice actually low frequency components as well as high frequency components. So it gives us better time frequency representation as compared to other existing actually other existing methods, and with good resolution at low and both high frequency components. And after that, now we'll see is 2 applications. One is automated alcoholism detection using FBSEWT method. So alcoholism actually is one of the chronic disease which is characterized by the uncontrolled drinking and preoccupation with alcohol. And it is one of the leading addictive issue worldwide. And more than 5% actually diseases, the global diseases, they are due to alcoholism. And it has many complications like mental illness, delirium, Wernicke-Korsakoff syndrome, irregular heartbeat, cirrhosis of liver, cancer, fatal alcohol spectrum disorder, and suicide. So detection of alcoholism is very useful for getting alert and take preventive measures. And traditional methods, whatever like questionnaires, blood test, and physiological tests that we use, they are non-invasive in nature, and they are invasive in nature, and they are less accurate, and they are painful. So of diagram detection using EEG signal based on the FBSEWT method. And here you can see nice framework that we have proposed. So we have EEG signals, then we apply FBSEWT method, and which actually provides you the components. Then we have used scaling operation to obtain more number of components. And then we have actually extracted features, line length, log energy entropy, norm energy entropy. And then we have performed the classification using least square support vector machine, support vector machine, and nearest neighborhood methods, which include training and testing. And using the leave one out validation method, it provides better actually classification between alcoholic and non-alcoholic EEG signals. And these are the actually features and their mathematical formulas to compute these features. So like line length, log energy, entropy, norm entropy. And the level of decomposition that we have selected, that is 9 for this work. And so total number of features will be 57. And these feature selection methods have been used actually for searching the most significant features, because most of the features, when we compute, there are many features, and if you select only significant features, it has many advantages. It actually it is useful for designing a real-time diagnosis method, real-time system, which can provide you more accurate diagnosis with less delay, less computational complexity. So several feature selection approaches, they include relief F, student t-test, relief chi-square test, correlation attribute, and gain ratio attribute are collectively used for obtaining the most significant features based on the majority voting method. And you can see from this table, most of the features that we have studied in this work, they are statistically significant. So they are highly suitable for the classification purpose. And we have used actually this top 5, 10, 15, 20% number of features. And so top 20 features have provided better classification accuracy. So you can see here accuracy, essentially specificity, performance measures. And when you go for highest top 20 features as compared to highest top 10 features, highest top 15 features, we get better performance and better classification performance. And then we have compared our method with other existing methods in the literature for the diagnosis of alcoholism using EEG signals. And from this table, you can see the proposed method, which is based on the FBA-CWT, and together with accumulated line length, log energy, entropy, and norm entropy, together with least square support vector machine classified, provides 98.8% classification accuracy, and which is higher than the other existing methods in the literature. So this actually FBA-CWT based automated signals analysis framework is used for detecting alcoholic non-alcoholic subjects, and most of the features, they are statistically significant. And to least square support vector machine classified with random with RBF kernel, that is actually the radial basis function kernel, had provided a better accuracy, that is 98.8% with top 20 ranked features. And after that, actually, we have studied the glaucoma diagnosis, glaucoma detection using two-dimensional FBA-CWT method. So this actually, you can see here, there's generally we use fundus images for the diagnosis of glaucoma and alcohol, healthy and glaucoma, these fundus images. You can see this cup to disc ratio becomes higher in case of glaucoma, and the doctors generally use actually this as a feature for the diagnosis of glaucoma. And so the person is actually suffering from the glaucoma, then this cup to disc ratio increases, and NRR neuroretinal rim, that actually decreases. So CDR and NRR values for healthy eye is around 0.2 and more than 0.1 respectively. And CDR values are 0.5 to between 0.5 and 0.7 for moderate glaucoma, and it's more than 0.7 for severe glaucoma. And this actually, here you can see there's a lot of motivation for detecting actually glaucoma at the initial stage. So here actually, like these methods, whatever we propose, they can be developed in the form of algorithm in the smartphone. So a smartphone will become really smart, and nicely you can detect glaucoma in the initial level using fundus images. So this actually is a very recently, a lot of work is going on towards in this direction, where people want to use machine learning and signal processing techniques for detecting this glaucoma using fundus images. So there are two types of actually glaucoma. One is open angle glaucoma, and second one is angle closure glaucoma. And open angle glaucoma is the most common type of glaucoma. And the symptoms that actually we can detect early due to this insufficient drainage of the eye. And if it's not detected in early stage, then it can cause gradual loss of the vision. And once you've lost the vision, then it is very difficult to recover, because it is also one kind of diabetic disease. So you can control it. So that early detection of this disease is very useful. So in this work, actually, we have studied open angle glaucoma, and angle closure glaucoma is rarely found. It is known as narrow angle glaucoma, and this is actually due to sudden blockage of drainage system of eye, which results in acute pain, red eye, and immediate loss of vision. And in this work, actually, what we have done, we have proposed this BSEWT method for two-dimensional case for image analysis. And then we have studied conventional machine learning algorithm like support vector machine, random forest classifier, and advanced machine learning algorithm like convolution neural network, deep neural network. And then we have compared these methods with the other existing methods in the literature. So for implementing this two-dimensional FBSEWT method, we have applied FBSE method, one-dimensional FBSE method, row-wise and column-wise. And once you apply row-wise and then you add column-wise and average it, then it is known as average row spectrum. And when you apply this column-wise and then perform averaging towards the row side, then it is known as average column FBSE spectrum. And then according to similar to FBSEWT, we design the this boundary, we perform the boundary detection of the average row spectrum, average column spectrum. And once you detected boundary, then we determine the components using the wavelet, empirical wavelet filters. And here you can see example, this is a toy image, and this is the Fourier transform, and FBSE based method is giving more accurate boundaries, more nice actually closed frequency components, and that is more suitable for the analysis. And this is actually, here you can see this is the RGB image of the fundus, and then we have green channel and processed image. So in the literature it has been shown that green channel gives you the better performance. So we have used actually green channel for this study. And it has some unwanted components, so we perform pre-processing of that image. So you can see that the detected actually detected boundaries and design filters in this figure, and where nicely you can see average row spectrum and for the 0 order and 1 order FBSEWT method, and this design detected boundaries and design filter bands. And these are the actually separated subband images using 0 order FBSEWT method for two-dimensional for first row, and second row shows the 4 subband images obtained using two-dimensional FBSEWT method when you are using first order Bessel functions. Then we have also used scale concept. So when you entire scale, and then that's really based on the and the corresponding filter banks you can see. And these are the actually obtained subband images corresponding to different scales, full scale, half scale, and quarter scale. And then actually the proposed method, we extract features from these components, then we apply classifier, and then it gives you detection between glaucoma and healthy fundus images. And this actually, for this study, we have used data set RIM1, R1, R2, R3, GS, Origa. And then we have used GLCM based features and histogram based features, and some central movement based features. And then actually we have compared this method also in the framework of this deep neural networks, convolution neural network framework. And for that, we call it proposed method 2. So here we take image, green channel, then we use two-dimensional FBSEWT method, then we use 4 subband images, then we apply residual network 50, then we perform ensemble and soft mix layer classifies these actually as a glaucoma and healthy images based on the deep neural network concept. And after that, we have compared this conventional machine learning and deep learning methods with our proposed method. And here you can see in both tables, when you use conventional machine learning and deep learning method, then our proposed method actually provides better classification between normal and glaucoma fundus images as compared to the other existing methods in the literature. So this is actually, there is a conclusion of this talk. FBSEWT method is a powerful tool for signal and image analysis, and automated detection of alcoholism, which is based on the EEG signals, can be used for the diagnosis actually diagnosis of alcoholism, and this method actually is based on the one-dimensional FBSEWT method. And diagnosis of glaucoma, recently there is a lot of actually scope to use time image for convolution neural network, and this time frequency representation that we have seen based on the FBSEWT method can be used as a tool to convert this one-dimensional signal into two-dimensional signal like images, and nicely we can use convolution neural network for such kind of signals. And we have seen real-time implementation of developed methods can be explored. And actually, this previous slide, due to time limitation, actually I could not explain, but the various parts of the methods actually they require very less amount of time to implement. So this such kind of features make such kind of methods which I have presented you to design in the real-time system. So with this, these are the references. Actually, this talk is based on these papers. For more detailed information about whatever I presented, please go through these papers, articles. And thank you very much for participating in this talk. And if you have any questions, it is my pleasure to answer them.